Hello everybody! So today we're going to talk about sound and sound waves, and let's start with what it is that we hopefully remember from when I first introduced this topic with a Slinky Spring. Is we just start with a simple thing, which is that sound is a longitudinal wave that needs a medium to travel through. So it cannot travel through a vacuum, and you're probably aware of that. It's because it's something to do with the fact that it travels through the collisions of particles. But as far as this lesson starts, this is what we know. Sound's longitudinal, and it travels through a medium. And this is a lovely statement, and you accept it as truth, hopefully, because you've been told by a teacher. But how do we know that? I mean, I can't see sound waves, because if I'm saying they're traveling through particles in the air or something, and I can't see the particles, this becomes somewhat tricky. So we're going to have a look at a few things of how we can see sound waves, and therefore how we can make measurements and how we sort of go about analysing them as scientists. So let's start with this. This is a simulation to show us kind of what's going on with a sound wave. So let's start this here. So what I've got is an image of a load of particles. They are all sort of like jiggling around in the air. Now, it's not strictly brilliant, because actually if they were proper air particles, they'd be moving a lot more than this and it'll be zooming around. But it's just to sort of keep sort of hold on them rather to be able to see them. And some of them are coloured red, and that's purely to give you a bit of some reference points to see things on. Now, we've got all these vibrating particles, and here we've got a speaker. Okay, and what do speakers do? Well, they just go one way, then the other. And so what they're going to do is give the particles a bit of a push. And so let's just send a pulse out and see what happens. Okay, so that comes out, and we can see that pulse traveling through. So each particle, you get this kind of like thing where things come in, and then there's a collision, and that collision gets sent out through all the particles. And what's useful to do is to then say, well, actually a speaker isn't just about sending single pulses, it's about sending repeated pulses. And so what we can do is we can turn to this and we can send repeated pulses out. And now what we've got is the thing that we start to talk about when we talk about what a sound wave sort of looks like. Because if I pause this, what you'll notice is that as this travels through, we get some areas where there are lots of particles. And then there's a place where there's not very many. And then there's another ring which has lots of particles, and then not very many. And these have some formal names. They're not essential for GCSE, but places where particles kind of are, they're called compressions. And where they're not, it's called a rarefaction, which is helpful because it's as if we didn't have enough words ending in shun in physics in this topic. And if I basically unpause and pause, what will happen is that these compressions will sort of move outwards as with the rarefaction. So unpause and there. See, our rarefaction is now there, the compression is there and there. And that's the wave traveling through the medium, okay, through these sort of repeated sort of collisions. So you've got particles that are moving somewhat randomly, and then we give them these extra sort of pushes that transmits that sound. And if we want to, what this allows us to do is to sort of overlay an image of what the waves look like. So I can actually say, so this is kind of an image of what we think the waves would therefore look like. The dark areas are the rarefactions, the lighter areas are the compressions where there's lots of particles, and we can change, what's going on. So we can change the frequency. So if we lower the frequency, we'll see sort of fewer of these being sent out, so these waves kind of the wavelength gets a bit bigger. We can increase the frequency and we make the wave sort of smaller. We get more of them, and that's what's going on at a kind of particle level. But again, this is lovely, it's a nice model, but we can't really take many measurements from this. This isn't a measurement piece of apparatus. You can't do anything with this perfectly. Ooh, side view, I wonder what that does. That looks literally the same. That's absolutely unhelpful entirely. So that is, just turned off, and so that's how sound travels through a medium, through the particles. So we can't, however, see this in the real world because we can't see the particles. So we need to have some kind of impact. Now, if you put your hands, if you make your iPhone or something play a noise and you put your hands near the speaker, you can definitely feel the vibration. So you will be able to feel the vibrations hitting things. And so what we end up using is we will send these vibrations into a microphone and we hook it up to a thing called an oscilloscope. And oscilloscopes, well, they're these things. The oscilloscope is one of the most useful devices in sort of history of physics because essentially it allows us, through the workings of it, which is quite complicated, it allows us to capture signals. And we can, the oscilloscope is basically like a kind of an early, sort of like computational unit purely about, although it's an analog thing, but purely about taking a signal and displaying it as a sort of a graph. And we can hook up almost anything to these various inputs. We can hook up ammeter, we can use it as an ammeter or as a voltmeter, but what we tend to do with sound is we will connect a microphone to this and it will enable us to get displays like this. This is hopefully something that you might have seen before, this kind of weird picture, because sometimes this is a confusion. People see a picture like this and they think that it sort of must mean that sound is transverse. No, this is us turning it into something we can see. It's what the oscilloscope allows us to do. And by connecting a microphone, what microphones do is that they turn sound waves into electrical signals, and then the oscilloscope will display it. And so that's kind of what we can connect them to. We connect microphones to oscilloscopes, we talk into the microphone, and we can get signals. And those signals will look like this. This is my voice. And so I've got my microphone, which is now my computer, and it's sending that electrical signal over the interwebs, over the glory of the interwebs, to this program, which is basically acting like an oscilloscope. And this is very sort of odd. Now, what this means is, well, the other big advantage of oscilloscopes is that you can freeze an oscilloscope at a time of your choosing, and by freezing it, you can kind of get a snapshot of what's going on at a particular point in time. There we go. So a particular point in time. So I made a noise, I kind of held it, and this is a freeze of that noise. And you can kind of see, oh look, there's a wave pattern here. There's a kind of repeating pattern. So essentially this is a graph. And much like sort of any other images, I can sort of measure this sort of height. It goes square at the top because I've gone beyond where if I go beyond outside the range it's expecting, it's got a sensitivity. If you go off scale, it's a bit like putting too much mass on a balance, it just goes flat. But I can measure an amplitude, and I can measure things in, but what am I measuring if I measure from here to here? And this is where, if you think about pictures, you might think, oh yes, I would measure peak to peak, I'd get a wavelength. Not so with oscilloscopes. The oscilloscope is something which is constantly changing in time. We're getting a measurement of time along our x direction. So basically this is like a graph where your y-axis is, formally it's measured in volts, but it can tell you your amplitude. Your x-axis is about time, and it allows us to measure the time, how frequent, essentially the time period of waves. So let's see if I can get another thing up, and I can go, ooh. There we go. So that was much better than just going ooh. So here is a picture of a wave, and let's say I want to know what is the frequency of this thing that I've generated. Well, my oscilloscope allows me to take a snapshot and I can start messing around with it. And the settings that are interesting are these ones down here. Seconds per division. Now that setting there is telling me that big square, how many seconds does a big square on the x direction represent? At the moment, 1 millisecond. And the nice thing about oscilloscopes is that you can change it. It's like a graph that you can modify the axes at will. Let's have half a millisecond. Oh, look, it's like zooming in. So now that distance, 2 squares, is what's representing a millisecond. And so I get zoomed in. I can do 0.2 milliseconds. So 2, 4, 6, 8, 10. So that distance now represents a millisecond. And I could get ridiculous. I go all the way in, like each one is 0.05 milliseconds. And at this, you can actually see I can't even trap a whole wave in there, so that's pretty pointless. I can zoom out and go to 5 milliseconds per division. So this whole thing here is a snapshot of that whistle for 5, 10, 15, 20, 25. So that's 30 milliseconds of that whistle. It's like a snapshot in time. And this is why oscilloscopes are really useful, because actually, even though they're very old pieces of tech and they're quite analog, you can change. If you want to measure something, you can take your measurement, and then afterwards you can start messing around with you can start messing around with what the scale is. So if you've ever had that annoyance where you've got some data and you're plotting your axes, and you suddenly realize afterwards that you've made a mistake with your axis, and you're like, oh no, it doesn't all fit. Well, brilliant. Oscilloscopes just allow you to change that all the time. Now, you can also do the same in the Y direction. So this is measuring in voltage because it's turned it into an electrical signal. And you can say at the moment this represents 5 volts. For a big square is 5 volts. But you can say, 2 squares, so that represents 2. So that's whole 4 volts is that now thing, and then 2, 4 that way. You can represent 1 volt, which is useless because it's now gone over the sign, or 10 volts, which is kind of useless because it's not easy to measure. It's not gone very high. So you can pick these things. And also, what's lovely, you've got these offsets here, which actually mean that if you're trying to take a nice measurement, you can move these things around so it's nice and easy to kind of, because it's easy to get it so there's a point where, oh look, let's take it when the wave, move it to there. So it captures this, and you can move it around. It's can only Photoshop really, but you can Photoshop the thing you're measuring onto the scale of your choice. And this is really nice. And what we find is if I play a song, I'm going to play a song with this. I'm going to play the best song ever. So some of you know what's coming. I'm going to play this, and you can actually watch you can watch an oscilloscope able to trap loads of sound, and it'll look like it's jumping around a lot, but actually it's because it's very rapidly going to lots of different things. So let's unfreeze the live input and let's play a song. The electromagnetic spectrum is just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves. Okay. So you're free to do that in your own time as well. So what we've got here is a really lovely sort of series of waves patterns. So I froze it at that instant. And encoded within here, in this oscilloscope reading, is all the sound that song encapsulated. All the magnificence of that sound at that instance of time, this is what it was. And there's loads in here. There is the voice, there's the weird drum thing, the weird piano, probably also the sort of the hiss of the actual thing, is the way it was recorded. But what we could actually do is you can sort of unpick these things, and you can take what are very complicated pictures and turn them into something that's a bit simpler. And so this allows us, oscilloscopes in, as they were in sort of physics and sort of like studies and things like that, is that you can try and pull apart different signals by taking measurements, and you can measure things independently. And also, this is kind of what you can then use to try, and if you want to remake a sound, say if you want to do early text-to-speech, what you could do is you take recordings of people speaking, and you try and see what kind of those waves would look like, and then you electronically try and recombine them in order to make sort of patterns that look similar. And we're now very, very sophisticated at it. In the early days, we weren't very sophisticated. So early text-to-speech had that very robotic voice, which you might associate with people like Stephen Hawking, because it took a lot of time to recreate sort of very complex speech patterns. Now, however, with processing power and stuff, we're a lot better at it. Now, at GCSE, you'll never, if you want to, please, the link for this is here actually. Please do feel free to pause the video and go and have a bit of a play. So play a song. I was going to play, a different song, but then I realised I'll probably get done for a copyright strike on YouTube. So do feel free to go to the link and play your own song down here and have a bit of play with this. Speak to it yourself. You want the live input and so on and so forth, because it's quite fun. Now, one of the things that we will do, however, is at GCSE you don't see waves this complicated. This is hard to interpret, hard to put them out. So it will always look kind of nice. So look, let's say. So you will always get waves that will look something like this. Okay, and what will happen is you'll get a picture and it will ask you something like, okay, what can you tell me about this wave? So I need to just move that back to where it should be. Yes, let's move it there. And I'll say, what can you tell me about this wave? What are the things that you can measure from a nice, simple wave of this type? Well, you can measure directly the amplitude. You measure from here to here. So you've got that, and this is, oh look, that's 1 square. So 1 square up. And then you say, okay, what does that represent? You have to check your scale, and if you go, oh, that's 5 volts is represented by 1 square, so the amplitude here is 5. If the setting was different, say it's 10, it's like, oh, okay, that is half a square, and each square represents 10. Half of 10 is 5. So you get the same answer. That's less interesting. What's interesting is being able to measure in the x direction, because this is going to allow us to work out what the time period of this wave is. So what we can do is we can say, okay, we've got our wave. Each square represents, we look at this, each square represents 2 milliseconds. And so what is one wave? Well, it's 2 squares. So 1 square, 2 squares. So that means that this time period is 4 milliseconds. The time period is 4 milliseconds, and that allows you to work out the frequency by using the relationship frequency as 1 over time period. So oscilloscopes are useful for us to generate the frequency of waves, of sound waves. And this is something we can apply even if we go well beyond the normal range of human hearing. If we go into the ultrasound region or the infrasound region, we can, microphones are still going to pick these things up. So we can measure sound waves, even if we can't actually hear them, we can measure sort of the result of the vibrations. So, so what we're going to do is I'm going to do a couple of little bits, or I'm going to work through some sort of problems. And so here we go. So this is interpreting the oscilloscope trace. So what we're going to do is we're going to sit there and try and work out. We're going to try for a few different things. We're going to measure we're going to try and measure the frequency of these things. So we're using an oscilloscope. So what you would get in a question, you have to be told what 1 square is in each direction. If they want you to measure the amplitude, you'll have that. And say, oh, okay, let's try and measure this. So, and the nice thing is I can draw on it. Right, oh dear, managed to draw everywhere, which is upsetting. So undo. Right, okay, so we've got 1 millisecond per division. Oh, I think this is the one I just worked out. We've got 1 square, 2 squares. So 1 wave is equal to 2 squares, which equals 2 lots of milliseconds, so 2 thousandths of a second. So that means that time period equals 2 milliseconds, and we can use the relationship as t is equal to 1 over f. So time period is 1 over frequency. That means that frequency is 1 over the time period. So we get 1 over 2 milliseconds. Now remember that milli is 1,000, so you have to do that's 2 over 1,000 seconds. So what we end up with is, oh no, this isn't the same one because I did 1 over 4 last time. So 1 over 2 over 1, and we get 500. So 1 over 0.002, 500 hertz. So that's what our oscilloscope can tell us. Here's another one. So we have 1 millisecond per division. We've got, so how do we work out this one? Well, what's unfortunate here is we're not starting in a nice sort of easy place. So we have to look at our screen and go, what do we have that is working? Well, let's look here. So we're crossing here. That's a nice point. So we can start here. And 1, 2, 3, 4, 5. Now this is nice here because here we've got 5 squares and we've got 1, 2. Okay. So what I know is in this time, which is 5 squares, is equal to, each square is 1 millisecond, so it is equal to 5 milliseconds, so that equals 0.005 seconds. I have 2 waves, so it's so we have 2 waves because we've got wave 1 and then we've got wave 2. Okay, so if I've got 2 waves in that time, that means I've got therefore 1 wave in 0.005 over 2, so that's 0.0025 seconds, and we can do, okay, so frequency is equal to 1 over 0.0025, and that gives us 400 hertz. Okay. Another one. This time we've got 0.5 milliseconds per division. So we're to say, okay, what's the best way of doing that? So we have, so there's 1 wave, so we can go, okay, so there's 1 wave, but it hasn't ended at nice in here, but I can then add this other half. So I've got this time of 1.5, I've got half a wave, full wave, 1.5 waves, so I've got 1.5 waves. How long? 0.5 milliseconds per division, so I've got 1, 2, 3, 4 squares in 4 times 0.5 milliseconds. So that equals 2 milliseconds. So that means that I've got 1.5 waves in 0.002 seconds. Have to divide that by therefore 1.5. And we get, okay, so that means the time period for 1 wave is 0.002 over 1.5, which is 0.0013 seconds. And it's certainly 1.1333 the recurring, but I'm just leaving it as it is. So frequency is 1 over the time period. So I do 1 over that, and I get 1 over which is 750 hertz. And then final one. So we have 2 milliseconds per division. So we can say, okay, so what's going on here? I've got one wave. Oh, I think this is the same one we just did at the start, just before I came here. So I've got 2 squares. So represents 2, 4 milliseconds. So 1 wave in 4 milliseconds equals 0.004 seconds. So the frequency is equal to the 1 over the time period. So it's 1 over 0.004. And we get 250. Yes, it is the one I did before I moved here. Okay, so that's the key with using oscilloscopes. The thing to remember is that unlike other pictures, this is essentially a graph where your x-axis is time. So you can't measure. So from an oscilloscope, you can only measure. You can measure the time period and hence calculate the frequency. You can't measure the wavelength from an oscilloscope picture, but it allows us to get images of sound waves even though we can't see them with our eyes. And that's how oscilloscopes work. So there we go. And there'll be an opportunity to have a little practice of solving some of these problems yourself.